Hi, Algebra 1. We're going to continue looking at quadratic functions. Now, instead of dropping objects, we're going to be launching them into the air. Here we go. In this problem, we have a cannon that is 10 feet off the ground. So we can see at 0 seconds, our distance above the ground is 10 feet. It launches a cannonball straight up into the air with a velocity of 406 feet per second. And there is no gravity, so it's just going to keep going up at that same speed. So after 1 second, it'll have gone 406 more feet, so it's now at 416 feet in the air because it started at 10. At 2 seconds, it'll go another 406 feet. Here's your table getting started. Again, we're just adding 406 feet each time. You can finish the rest on your own, but when we get to t at the end, this is where we're writing the equation. It's the same thing. Since we're adding the same thing each time, you're going to want to make a note here that it's linear, and I'll give you a hint. Remember, linear is y equals mx plus b. In this case, we're using d for our distance. Our m is going to be our slope. How fast is it changing each time? So that's 406 times s for seconds instead of x, plus our starting point, which was 10. So that's the same as the equation down here. Now we have a table showing that same cannonball, but actual heights with the effects of gravity included. So we start out at 10 feet above ground level, and then you can see how the height is different than what we calculated earlier without gravity. Once you graph them, you can see that without gravity, the cannonball is going to go higher. With gravity, it starts to level off. We see this curve happening here. So we're going to write an equation to model the actual distance. So that means including gravity. So what we're going to do is we're going to start with the linear model that we just had, where we started at 10 and we went 406 feet per second. So that's t. But now we're going to add in the effect of gravity. And so that's going to be minus 16t squared. It's subtracting because when we launch something up in the air, gravity is going to be pulling it back down, so it's making the height smaller. So we're subtracting off t squared. And this 16 should seem familiar from the last lesson, where we saw that 16 was the effect of gravity, the acceleration due to gravity on Earth, 16 feet per second per second. And this is your equation. So this first part you can think of as being without gravity, and then when we add in gravity, we just have to put that acceleration due to gravity on the end. So now when you see an equation like this, it is a quadratic because of the squared term, and we can pick out what each piece represents. So 50 was the initial height. 312t, that means that it was launched at an initial speed of 300 feet per second, where t is going to be the number of seconds. Remember, this first part was our linear function when there was no gravity. And then negative 16t squared is showing us the effect of gravity. And that negative 16 is representing the feet per second squared. We're subtracting it because it's pulling it down. Here in Desmos, I have graphed my function. Notice I have to use y equals, and then I have to use x in the equation instead of d and t. Desmos doesn't like other variables. But right now I just have this red line that seems to be going almost straight up and down. The problem tells me to adjust my graphing window to different boundaries. So I'm going to use the wrench, and where it says x-axis, I'm going to change that to go from 0 to 25, and then I'm going to change my y-axis to go from 0 to 2,000. So that's how you can change your window. You can also pinch and zoom right on the axes, but this is one way to get it to be exact. So now I have this parabola that is showing the path of this cannonball. The shape of the graph is a parabola, and that tells us that the cannonball went up into the air and then came back down. If you remember, the problem said that it shot the cannonball straight up in the air. So this is not showing us the visual path that we would see the cannonball take. The graph is just showing us where is the cannonball, how high is it in the air at certain times. So for example, at 5 seconds, I could see the cannonball would be this high. We're estimating here the maximum height seems to be about 1,570-ish feet, maybe 80. And then when does this happen? It's happening right before 10 seconds. So probably at about 9.8 seconds. When does the ball hit the ground? That's out here, I would say at about 19.6 seconds. And I know that because that's where the height of the cannonball is now 0, so it's on the ground. Last one, what domain is appropriate for this function? Domain is referring to all of your possible x values. So I can see on my graph that it makes sense to go from 0 to about that 19.6 seconds. Remember, because our x-axis is representing time in seconds. When they say appropriate, that means what makes sense in this problem. It doesn't make sense to go into the negatives with our x values because that would be negative time. We're not going to go back in time. And it doesn't make sense to go beyond 19.6 seconds because when the cannonball hits the ground, it's not going to be going into negative y values. In your lesson summary here, there's a lot of words going on, but there's some important things to help you out. First, when we have a quadratic function like this, that first part of the function is the linear part. That's telling us what would happen if it had no gravity. So in this case, we're starting at a height of 5 feet, and we're starting with a speed, a velocity of 60 feet per second. That's the slope of that straight line if there was no gravity. Then your negative 16t squared represents the effect of gravity, which is going to cause it to slow down and then fall back down. That's why it's negative. And we've seen this term before, vertex. Vertex is going to be that peak at the top of the graph, or it could be, if it's a parabola going down, it could be at the bottom of the graph.